Jai Hind to all. My name is Dhanshri Parihar, Assistant Professor, Department of Computer Science and Engineering, Akgec Garg, Engineering College. And my today's topic is modes of transmission in input-output devices from the subject Computer Organization and Architecture. So, today we are discussing how these modes of transmission will be, where the data will be being transferred with the help of direct memory access, that is the DMA, how the input-output processor are worked, how they will be connected to our system for the transmission of the data between the devices, and what is the serial communication. As previously we have discussed already the modes of transmission. In modes of transmission, we have discussed the programmed input-output transmission. So here in modes of transmission, the program input-output, we are having an interface connected in between the CPU and the input-output devices. So there will be a drawback of this scheme. Now what is that drawback? In this scheme, the CPU needs to perform a lookup in data register again and again for the checking the availability of data, due to which an add-on delay time will be there in a CPU processing. So the execution of CPU will be assumed to be slow in this kind of scheme, as the CPU need to perform a lookup again and again in a data register, and to stop it, we can say present work for performing this lookup. So this scheme is slow for data transmission. So to avoid this condition and to remove this drawback, the another kind of transmission will be used, that is a DMA transmission. In a DMA transmission, a DMA, that is a direct memory access controller chip, is being used. Now what is this DMA chip? This DMA chip will be working independently. So here whenever the data transmission needs to be done, CPU will be not the part of that transmission. The transmission is being done by the direct memory access controller chip between the input-output devices and our memory. Okay, and the CPU will be doing some other tasks. So all the role and responsibility by the CPU is given to the DMA to perform this transmission. So how this will be possible? So in a DMA chip, we can say that it is a controller chip that will be having this DMA select signal. We are having that read select reading signal. Okay, then we have write signal that is indicated by WR, and then we have a bus request, bus grant, and interrupt signal. So these are certain signals which are the part of this DMA controller chip. Along with this DMA controller chip, 3 more registers: address register, word count register, and the control register is being used. Now what is an address register? That contains the address to specify the desired location in the memory, where we need to put the data, or from where we need to get the data. Now another is the word count register that holds on how many words hang. So to calculate the number of words being transferred between the memory and the input and output devices, that count need to be stored in a word count register. So what is a control register? It will specify the mode of transmission. Either it is in a reading mode, writing mode, either we are reading the value or writing the content to our input output device. So this is we can say the common signal which are important part of this controller chip. Along with that, we have some external signal also. We have a DMA request signal and a DMA acknowledge signal. So let's have a look how this DMA is performing a transmission between the input output devices and our memory unit without using the CPU. Okay, so we have a 4 block connected over here. As we can see here, one is CPU, one is the memory unit, one is the DMA control, and another is the input output peripheral devices. So transmission is between these two, and how this transmission is being performed. So that is this thing is all about that. So whenever the input output device need to transmit the data, it will be putting the request on the DMA request signal. It will be sending that request through this signal, and that request is being received by the DMA controller chip. As we can have a look over here, we can see that we are having certain signal. This is the data signal. The data signal that is used to transmit the data between the data bus. Either from here to two-way transmission is there. Either to put the data on the data bus or to get the data from the data bus. Another is the address line, which is used to put the address of the input output devices or to obtain the address from our address bus, this one. Next one is the write signal, WR signal, that is used to perform a writing operation into our RAM memory like this, or add to perform a writing operation inside our input output device. Okay, read to read the content from the memory and to put in the input output device. Then we have a DS, that is a DMA selection chip signal that is used to select this DMA controller on behalf of a CPU. Then we have a this reads read the DMA, select the DMA and then perform some read operation. BR is the bus request signal that will be given by the DMA controller to our CPU. Then we have a bus grant signal which is being given by the CPU to we can say DMA controller in response of bus request signal. Then we have an interrupt signal which is being given by the controller to our this CPU. That is an indication that to the CPU that the DMA need its judgment, and it will an indication to the CPU to have a look on the DMA what the DMA wants to perform now. So let us have a look how this functioning will occur. Okay. Now first of all, whenever the input output device need to transmit the data, it will put a this DMA request signal in a high mode. Okay, indicating that this will be now active and this signal is given to this DMA controller chip. As soon as the DMA will receive this signal, it will be generating an interrupt signal indicating the CPU that so there will be some important thing that DMA wants. Okay, so CPU will be halting its currently running task and it will be performing a lookup for DMA. So what DMA is asking. Okay, then the DMA controller will send a bus request to the CPU. As we all know that the CPU is the brain of computer system and all the, we can say all the devices are being controlled by the CPU. So DMA is itself is not sufficient to get the control of all this bus. This all buses, control bus, this control bus, data bus and address bus, this will belongs to CPU only. So the CPU is the owner of all these three buses. Whenever the DMA wants the control of these buses, it need to place a request to the CPU asking the permission to get the control of these buses. For that purpose, it will be sending a bus request signal, and in response of that, the CPU will be sending a bus grant. So it is obviously totally depend upon the CPU whether it wants to give that bus request to the bus grant to the DMA or not. If the bus are busy with the CPU, it will be not giving any grant signal. It will be putting it to be a zero mode. Whenever it will be sending a one high signal in it means it is indicating to the DMA that now buses are completely available for the data transmission. Okay. So whenever, as soon as the DMA will get a bus grant signal, what it will be doing? It will be take the charge of all the buses and thus allow input output devices to transfer the data from here to here directly. Okay. So that indication is being given by the DMA as an acknowledgement to the input output devices that now the buses are now available and you can directly put your data. Now CPU is not using this. So it will be opening all the buses for being used by the our peripheral devices. So this is the way how this DMA will be working on behalf of the CPU. At the moment when the data is being transferred between the DMA and the input output devices, the data is being transferred from the input output devices to the RAM and the DMA is having the control of all the three buses, the CPU will be busy in performing some another task. So the CPU utilization is high in this kind of a scheme. Now in this type of a scheme, we have two type of transmission over here. One is the burst transmission and another is a cycle stealing phenomena of a DMA. In a burst transmission, a block of a sequence of a words means a very large amount of words are being transferred between the by the DMA controller chip between the memory and the input output devices. So the DMA is busy in transferring the very big block of data between the DMA, taking the advantage of all the buses. So that kind of transmission is known as the bulk transmission of data, that is known as the bus transmission. This mode of transfer is needed when we need to transmit the data in a very fast mode, or we can say when we are having a very fast devices connected to our system like magnetic tape and magnetic disk. Okay. Then we have another kind of phenomena associated with DMA, that is cycle stealing phenomena. So these two topics are very important from a competitive point of view in a DMA controllership. So another phenomenon is cycle stealing. In a cycle stealing phenomena, it is a technique where the DMA controller will request only one data per word at a time to being transferred from the CPU. By stealing one clock cycle of a CPU, we can say. Suppose we have a CPU is working on a 10 clock cycle right now. It will be transferring the data for 10 clock cycle. Now, it when the DMA will place a request that please give me one clock cycle. So, I will be getting the control of buses and I will be frequently transmitting the data for only one clock cycle. So, you can give one clock cycle to me and I will be using it perfectly and moving the data from the input-output devices to our memory devices. So, that phenomena is known as a cycle stealing phenomena, where the DMA will get the control of only 1 to 2 clock cycle, that is in a continuous phase of a CPU, and steal them and transfer the data immediately and return the control of buses to our CPU. So, it is known as a cycle stealing phenomena. Okay, so these two are very important. So, this is all about our DMA, how it is working. Now, next is input-output processor. So, as we all know, we have a CPU in a computer system, that is a central processing unit. We have another type of processor in a system which is known as a input-output processor. Now, what kind of processor it is, what kind of functioning is being performed by this processor. So, this processor is a direct memory access capabilities. It will be having a direct memory access capabilities. So, there is no need of putting a pressure on CPU again and again. So, we have a dedicated processor which will be working only for the input output devices and the data transmission and all. So, there is no need of putting a load over our centralized CPU. Okay. And it will be having a direct memory accessing capabilities. Then we have a channel access memory by the cycle stealing phenomena, unlike DMA controller. So, this scheme is totally different from DMA. DMA is a controllership. As we all know that the processor and the controller is having a different application. The controller is limited in functioning and the processor is very, we can say, a multiple tasking instead of our controllership. So, here to remove the drawback of DMA, so it is limited in functioning, a processor, a dedicated processor named as input-output processor is being introduced. Okay, to replace this DMA. So, the instructions which are associated with input-output processor are known as input-output processor instructions. So, to overcome this DMA controllership, to remove this controller concept, here the IOP is being used. So, what is the functioning of this IOP? As we can see in this diagram, we have a memory unit, we have a common memory bus, we have one central processing unit CPU and we have a input-output processor which is connected to different peripheral devices. Although it is being connected to this peripheral devices, it will be acting as a intermediate between the memory unit for transmitting data between this peripheral devices and the memory unit. Here the CPU is totally, we can see, free from this transmission. It can be parallelly do its another task also, but it doesn't mean that it will be not holding any kind of control over these processor. CPU is capable of having control on these peripheral devices also. So, whenever the data transmission being requested by the peripheral devices, it will be put on the transmission is done via through this IOP, and IOP is transferring the data that indirectly to our memory unit, or getting the data or putting the data into the memory. So, data gathered in IOP devices, we can say IOP at device state and the bit capacity while CPU executing its own program, and the transfer between the IOP and the device is similar to the program input. It will be like putting the interface between the CPU and the input output devices. Then the transfer between IOP and memory is similar to the DMA controller. But what we are doing, just we are replacing that controller by now a microprocessor over here. That is just a difference. Then the CPU is the master, that I have told you earlier, that although it is not directly communicating with the peripheral devices, but still it will be a owner of all the devices in the system. Okay, just this technique is used to keep this CPU free from this transmission and doing some another execution. So this is all about this transmission. So let's have a look how this transmission occur. Whenever the transmission need to be initiated, the CPU first send an instruction to test whether the IOP, that input output processor, is available or not. So the status, the transfer status word in the memory will be indicating its availability, and if the status is okay, that is either it is 0 or 1. 0 is indicating that is not available and 1 is indicating that the processor is available. If the status is okay, then set the starting input output instruction to the IOP and then access the memory from this IOP program. After that, conduct the input output transfer using DMA or without DMA, and then complete the transmission without interrupting the CPU. The CPU in parallel will be continuing another program when it is busy in transmitting the data, when the IOP is busy in transmitting the data. Okay, in that moment the CPU is doing its own task. So whenever it's complete its execution, it will send an interrupt to a IOP. We can say request to CPU, indicating that now the data transmission or that operation has been completed and the transmission status word of the memory word is being changed, and then the that status word has been checked to know whether the correctly data has been transmitted or not. So this is the way how this CPU processor and IOP processor will work together in our computer system. So this IOP is generally used to a kind of a helping hand with CPU, not to involve CPU in data transmission. Small tasks like data transmission among the input output devices and the memory. So this is another scheme which can be used on behalf of DMA and input output programs. So these are the three schemes of modes of transmission. So there is another one topic known as interrupts. Now what are interrupts? Interrupts are generally an indication, we can say, by a software or a hardware to a system, to a computer system or CPU, that to hold the currently running task and to focus on the task which is sending an interrupt. So if that task is a higher priority task that need to be operated first, that is a role of interrupt. So we have a first type of interrupt which is known as a priority interrupts. Now what is a priority interrupt? A priority interrupt is a system that establishes priority over the various sources to determine. Suppose we are having 3 to 4 devices connected in a system, like we have a mouse, we have a keyboard, we have a printer. So how the system is going to decide which one, whose request is being accessed and to be functional first? So it is not on the basis of first comes first serve. It will be on the basis of the priorities. So there are certain priorities set to those particular devices, and then on the basis of that the particular device is being served. The very first technique for priority interrupt is the polling technique, or we can say it as a daisy chaining polling technique. Now what is a polling technique? Here in a polling technique, as we can see in this diagram, we are having certain devices connected in a sequence. Okay, in a polling technique, the device number 1, we can say, is having the highest priority in the sequence, and they are connected in a chain-like structure. The second device is having this second priority, and third is having third, and so on to n devices. So whenever an interrupt is being requested by these 3 devices in a connected in a parallel, suppose the device 1 is also generating a request, device 2 is also requesting, device 3 is also requesting. So to whom the CPU is going to be served first? As we have said that the device 1 is connected in a first priority in this block diagram, so it will be having the highest priority among all the 3 devices. So at a moment when the 3 of them are generating the request to the CPU is going to serve to the first one by default. We can see this connection. Okay, so it will be sending an acknowledgement to the first one. So whatever task the device 1 want to perform, it will be performing. So PI is the input, we can say priority input, and this is the priority output. Whenever it will be connecting to it, it will be inserting here 0 and here 1. 0 means priority output 0 means no signal will be transmitted further till this device will complete its task. So when it will be getting it, the PI will be getting it, and it will be continuing its task. when it task will be over, it will be opening it, putting it to 1 value. So when the value of PO is 1, the signal is transmitted to next device. Okay, similarly for when it will be 1, it will be put it to 0. When it will be closed, it will be put to 1 PO, that is priority output, and the device third will be receiving the signal for its, we can say, indication for its execution. So this is the way how these devices are working in a sequential priority. The highest priority devices is connected first in the circuit, then the second one, third one, and so on to n term. This kind of priority is known as the daisy chaining priority. Okay, so it is a hardware, it is a part of a hardware priority interrupt. So in a hardware priority interrupt, the interrupts which are being generated by the hardware devices, okay, that are hardware priority interrupts. So this kind of scheme is being used for serial hardware priority functioning, for interrupt request lining, and for the interrupt acknowledgement lining. So this is known as the daisy chaining priority. Now the next kind of and for doing so, we will be having a vector address also over here. So VAD is the address, individual address of each device, we can say. Whenever that value will be high, that will be put in on this line, and how the CPU will come to know that which device is generating a request by these vector addresses. Suppose VA2 is sending a request, then the CPU will be receiving only the vector address of the second device, okay, from this line, this address line, and it will be servicing an acknowledgement. So by default, the device 1 is always receiving the first priority in the circuit. Although the device 2 is generating that request, here it will be putting 1, then it will be 1. It means that both line is open now, and it will be going further to device number 2. Here it will be 0 indicating man it is a closed circuit. For further, the signal will be not be transmitted and being served by the device number 2. So that is the indication, this kind of scheme, how it will be working by using the vector address. Now next type of interrupt is the parallel priority interrupt. Now in the previous scheme, the priority is on the basis of the connectivity. The first in the device in the circuit will be having the highest priority. Now in this scheme, all the devices are connected parallelly, and they have a fair chance to get a priority for their execution, for the task given by that devices for their execution. Okay, so they are connected in a parallel. As we can see over here, we have a disk, we have a printer, reader, and keyboard. They are connected parallelly, and we have a AND gate over here where we have a 0, 1, 2, 3 and maskable bit, that is the second input over here. So whenever the disk will be generating, the value will be 1, 1, and the ending of 1, 1 will be always 1. So this will be, all will be sending 0, 0, 0, 0 and 0, 0. 0, 0 either 0, 1. Okay, the ending of 0, 1 is always 0, or the ending of 0, 0 is also 0. So it doesn't matter the masking bit is having 0 or 1 value. If the printer is having this generating to be 0, then the masking register will be always second input will be generating the 0 only. So at a one time only one interrupt will be generated by the parallel connected we can say devices. Okay, so when disk will be generating a request, it will be putting it to be 1, and the maskable register is also putting it to be 1. Okay, then this interrupt is going to be functional, and all the other, if it will be putting 0 from the masking bit, it is 0, 0 and 0. There is it will always be producing 0, 0, 0 like this. Okay, so at a moment only one signal is being active, one interrupt is being activated. So all have fair chance of getting selected. There is no priority. If printer is doing so, it will be gaining it from I1. Reader is doing, keyboard is doing, so they will be parallelly executing. Here we are having a vector address buffer to the CPU indicating to which device it will be going to serve. So whenever this I0 is putting in some other values coming to be 0, that will be becoming 1 and X will be becoming 0, and a vector address is being generated over here. Okay, and that vector address is belong to some device. Here we are having the interrupt enable and interrupt status bits indicating that whether the interrupts is need to be sent to the CPU. Enable bit will be indicating that the address which is obtained in this vector address machine is going to have, and that address is being located somewhere for some input output device. Here the interrupt to the CPU means it will be going to interrupt the CPU for that corresponding address of an input output device. Then we have an acknowledgement to the CPU. If the CPU is serving that interrupt, it will be sending a acknowledgement signal plus the status signal and forming an enable bit. Okay, so that is all about this parallel priority interrupt. Thank you and Jai Hind to all.